Alrighty, hello folks. I am Julian Kummer and I am here today talking to you about PipelineC, easy open source hardware description between RTL and HLS. Big thanks to the workshop on open source EDA technology 2022 for hosting me here. I think it's WOSET, maybe WOSET. I'm very excited. It's going to be like, woohoo set. Here we go. I want to hit you with, intro, what is PipelineC? Is this some kind of hardware description language, RTL, a generator of some sort? Is it a high-level synthesis? And then we'll discuss fundamental building blocks, basic use of the tool, get into some advanced features, and I have a nice demo for you. Alright, so we do these things not because they're easy, but because we thought they would be easy. And apparently this is a meme from the internet somewhere, and apparently was my thinking in 2014, 2015 as well. I was working as a FPGA engineer, and I was seeing how annoying it was to write hardware description language, especially regarding timing analysis and needing to move logic around from cycle to cycle, or pack logic into a cycle, or unpack logic from a cycle, all kinds of different pipelining. And I thought, surely I can make a tool that's easier than this, right? And what would it take? A few months of hobby time? A year? I mean, just look at how easily pure functions map to combinatorial logic, right? So, hardware description languages know this. VHDL and Verilog both have a function that you can write, and in Verilog, you use blocking assignments, and it looks a lot like C, and a lot of people like to say, I like Verilog more than VHDL because of how C-like it looks. Well, you might really like this then, perhaps, because PipelineC combines functions and modules that you would think of from hardware description language. So, looking here at an example, a simple function turns 8-bit unsigned, takes an 8-bit unsigned, and not really filling in the body of the function here, just the top level, and on the right here is generated VHDL from PipelineC, and you get a module with the same name as the function, input ports matching the input arguments, and only one output port because C only allowing one return value. And so what that ends up meaning is a lot of your return outputs are structs with multiple fields. And PipelineC here mostly cares about the delay across this logic. It's going to know, the inputs and outputs, and mostly it's looking at it as just a, blob of LUTs on an FPGA. All right. So those same chunks of combinatorial logic can be auto-pipelined by splitting the data flow with registers in the appropriate location. At this point, it's still seeming pretty easy in my mind. I'm an FPGA engineer. If I can pipeline logic by hand, surely I can write a tool to do it. I just want to, say, hey, I'm using this FPGA, and I want to meet this operating frequency. Then I write a little bit of C code, and I just want a pipeline out the other side. And so I didn't know this at the time, but HLS tools can also do this, and they'll go further for sure. They'll do fancy derived state machines alongside the pipelines. They'll get an AXI bus in there, tie it up to some block RAM, kind of all inferred for you. But PipelineC is just more hardware description. The body of the function describes the data flow that you would expect. So here, these two floating point values come in, and you're doing a selection between whether you want to multiply them or add them together. And that forms this kind of data flow here, where fun floating point addition taking longer than a floating point multiply. And so where the pipeline stages go here in blue might look like that, with a few stages for the multiply and the first part of the add, but the add takes longer, and you need delay the output of the multiply a few cycles, all the while delaying the select all the way to the end, where you have the results of the two that you're doing the mux between. All right. So to get started with PipelineC, you only need one or two pragmas here. The first one being this main megahertz that you saw on the last slide. You're giving what is a top-level function name. So your function input and return output are top-level inputs and outputs. Like that would go off chip, things like that. And then you're specifying an operating frequency. So you're saying this is going to run at 100 megahertz. Most functions don't actually specify a frequency. Instead, you're using a function inside of another function, or this is nesting modules here, so modules inside of modules, and you can infer intended clock domains that way. PipelineC functions are only one clock domain. We'll talk about multiple clock domains later. Right. So, oh yes, I wanted to say these main functions don't actually even need to have an operating frequency because of their links to other main functions. You can also infer the frequency you intend. So, second pragma here is the FPGA part. In this example, it's Arctic 7 series 100T from Xilinx. And this is important because different FPGAs can have different timing characteristics, and they have different built-in primitives like DSPs and multipliers and such. And so picking pre-pipeline blocks, kind of one size fits all solutions, and working with those can often be over or under pipelined, which is at my job when I was discovering the troubles of pipelining, we weren't using building blocks because we needed custom, down to the cycle control. Alright, so what kind of output do you get from the tool here? We have this myfunc math function from the previous slide in this C file now, and you're going to run a command line like you see here at the top. It's producing VHDL. I showed before that functions are modules, and so what you get here is at the very, very top level, your main functions get exposed. So we had tagged myfunc as a main function, so its inputs, the x and y, and select appear there, and then its output is also there, its return. And so, what's actually inside here is a pipeline of initialization interval equal to 1. PipelineC doesn't produce any other initialization intervals. Like I mentioned earlier, some HLS tools can do that, but that's not what PipelineC is doing. It's as needed pipeline to meet the operating frequency. So, aiming for a not over or under pipelined situation, which is right on. The tool also generates scripts that help you bring these VHDL files into Vivado or Quartus. And there is also another layer you can strap on here, which is a conversion to Verilog, which makes use of GHDL, the GHDL plugin for Yosis, and Yosis to do another great layer of code generation there. A lot of folks are concerned about the quality of code generation, and I think the PipelineC VHDL looks pretty good. I describe it as human readable. Maybe debate what kind of human you might need to be. But on the other hand, the Verilog that comes out of the GHDL and Yosis process can be a little bit harder. Things get put together and you end up with one kind of file at the end that can be a little daunting. Anywho, at the bottom here is showing what the tool outputs text-wise, the description of your function, what you targeted, what it ended up reaching. In this case, it took 5 clock cycles to do that. The multiplies and the multiply and the add and that bit of select with the mux all split across 5 clock cycles to meet timing, and then it gave you a tickle script here with the VHDL files, and you see ... we're starting simulation next. So right. What kind of simulation support does PipelineC support? So first off, you can sort of say, and it's encouraged to compile some of this C just with a C compiler. That math function from before, you could easily get that to compile with a C compiler and do all sorts of tests and test vector generation and checking, and it's very easy to get in a situation where you're simulating by kind of writing a C program, and then parts of that C program end up being the hardware description. But of course, the VHDL that comes out of the tool is also completely synthesizable, and so it simulates across all simulators, and it's reliable. It doesn't use any weird simulation-specific constructs that wouldn't synthesize anyway. Right, and it generates templates for some of these tools listed here, and you see some of the command lines here over here on the right. At the bottom here is what we got to opening up Model Sim in the earlier example. Model Sim opened, and I just went in here and forced a few values for you and clocked to the clock, and you can see the 5-cycle latency, and works that easily. Right. So I want to take a second here to pause and get to a contrary here. What is PipelineC not? And a bunch of pictures over here on the right of some fantastic tools, and that aren't really what PipelineC is getting at. So it's not a full high-level synthesis tool. There's not anywhere near arbitrary C code getting into this. There's no global shared memory model, so you can have pointers and dereferencing memory and stuff like that. There's no threads here, anything like that. And this isn't a compiled C-based simulator. I mentioned in the last slides that you could take parts of PipelineC and compile it with a regular C compiler. But the entire design, multiple Hawk domains, and if you want to, you can insert chunks of IP and raw HDL that you have sitting around. It doesn't have to be all PipelineC, so that kind of stuff wouldn't make sense to just compile with a C compiler. But again, the parts of PipelineC code can absolutely be compiled by C compiler, and it's encouraged and has been used to great effect. PipelineC is not a metaprogramming hardware generator kind of system. It of course uses the C-type system and preprocessors, so nothing fancy going on there. You hope you're not going to be coming to PipelineC for its advanced type system. And it's also not a stitching tool. So it's not just made to, I have these set of modules, I need to link them up to a bus or something and, spit me out a system on chip, or it's not doing any of the top level kind of instantiating PLLs or doing anything with clock networks. It doesn't know anything about the top level pin assignments you have out to your board or anything like that. It is doing synthesis and placing them out in the background, so you do get some of that out to use, but actually getting a bit stream out of your tooling is still left to the user. After 2 or 3 years of getting that auto pipelining to work, I came to an old professor of mine, Dr. Taskin, from Drexel's College of Engineering, Electrical Engineering, and he said it's very nice, but is pipelining all that it can do? It can do other architectures, maybe state machines, maybe. And all these examples up until now have been pure functions, combinatorial logic. They don't maintain state. So no, I had to say no, I can't do that. And of course, it's been off making it do that since then. So PipelineC is a hardware description language, and like I said, it started off as just for combinatorial logic and auto pipelining, but now it's a full hardware description language. Said a bit here that it's not full regular C. You can't just compile the whole thing and expect it to work as hardware in C, but parts of it can be compiled by regular compilers, and it's great for a kind of simulation during development. It can reasonably replace Verilog and VHDL, and it produces synthesizable VHDL, and I like to say it's human readable and debuggable. I mentioned that you can insert raw VHDL chunks and blocks, use that to instantiate IP you have sitting around. So, the main bit there is that autopipelined is now just one of many features in this area between RTL and HLS. Just a few more general thoughts here about what PipelineC is trying to be versus what it might not be. It's more about functionality inside the module, describing the hardware's intent, or design rather, intent. I'm sorry, jeez. To say describing the hardware, not the intent, so you can't just say, I want to multiply these two matrices. You're still going to have to write the hardware describes, some kind of matrix multiplier and shuffling data into it and shuffling data out. Things like state machines, pipelines, of course, getting block RAMs in there, DSPs, multipliers. It's not that I'm in love with C, but it's certainly easy, common. It's low level enough where higher level language constructs aren't, becoming confusing into what's synthesizable or what's not. And I've mentioned, of course, that it's compilable, so that makes for really good simulations or emulations, you might say, during development. And overall, I'm just trying to make RTL design easier. All right. More general thoughts here that PipelineC is less about purely stitching things together. Like I said, it's not doing a build a system on chip kind of thing, generating a bunch of software and a bunch of hardware together. It's not all about a central bus and a bunch of things address mapped to it. And it's not just about I want to have C code and get a bit stream out the other side. It doesn't do the full flow there. And it's not to say that PipelineC can't or won't do any of these things. It's just not the active focus of development. I do see some great related features here of tools that I hope to continue seeing progress on. That stuff folks might be familiar with. LightX, FuseSock, you got Silicon Compiler coming out, Defiant Remote, and Sabana as some of the cloud FPGA related things. I see a bright future for all of that. I also see a room for some kind of a block diagramming tool. I don't know if there's a popular open source FPGA related block diagram tool, and lots of folks have mixed feelings about Vivato's block diagram tool, or whatever Cordis's is as well, and they don't work well for all designs. But for a lot of designs, they do work well. You do just have a few pieces of IP that you're kind of dropping down and linking together, and off you go. And so, to the extent that that area is workable, something like a GNU radio flow graph looks like a perfect candidate as something to start with, maybe. Right. So, all right. Back to PipelineC after giving this kind of origin story here, trying to provide context of what PipelineC is or isn't, and right, I want to continue exploring how it's a full hardware description language here, and getting into the next bit of fundamentals with using this state and state machines and registers and things like that. So I had come from this place where I had combinatorial logic and was doing autopipelining, and I had the functions body giving me a data flow graph, and I needed some kind of C concept that would map to this function is occurring multiple times, called multiple times, you might say, but there's some kind of state that's sticking around, and static local variables seem like a natural fit. So you could picture these functions as running multiple times, each time being a tick of the clock. It's all synchronous here, and rising edges in the back. Right, so register transfer languages know this. Clocked processes, state machines from Verilog and VHDL. But here, you're giving explicitly what you want to be registers or not. Oftentimes, processes and Verilog VHDL, you can get a little bit tricky about what infers a register, which is what doesn't, but PipelineC, it's very clear. And like I said, you could picture the function as just being run multiple times in your head as kind of the way to simulate clock by clock. Two important points here I want to get at, that this is something that's not like regular C, in that each function call, each location is a new instance. So with regular C, your static little variables are around for multiple entries to the function, but here each time in code that you call a function, it's a new instance, and that static is just for that instance. And then down here at the bottom, these functions don't auto-pipeline. In here, it's a pretty simple transfer function with this add here, barely making a state machine here with your counter. But you can certainly have more and more complicated data flows that are not easy to pipeline with feedback like that. So when you write something like this, yeah, you're not going to get any sort of funny business with trying to infer initialization intervals not equal to 1, or like in state machines with extra states in it. It's just registers and combinatorial logic. Alright, so how is PipelineC able to do the auto-pipelining that it does, and what kind of timing feedback can it give you if it can't auto-pipeline things like in this static counter situation here? Well, at the time I thought, how do I, an FPGA engineer, know how much logic can fit into a clock cycle? And it involves becoming familiar with your synthesis and place and route tool. And so PipelineC builds up a library of operators, functions, and all sorts of things, and knows combinatorial delays of stuff. And so working with many tools here, Vado, Horus, Lattice, and the open source tools, that's fantastic to be able to work with. Had a little bit of time to play with the Finite tools, and some fun ASIC timing models as well are supported. All of those tools can be run, and you can say, give me the combinatorial delay across adding two 8-bit numbers here, this binary operation, the plus between two U and 8s. And they'll say, the path delay is 2.2 nanoseconds. But you can also switch it up, and earlier I showed some float types. You can ask the same thing, and it'll tell you, that's closer to 19, 20 nanoseconds. And what the tool is going to spit out for you is, you say, I want to meet some high operating frequency, and as a sort of beginner to these sorts of tools, you just fail timing and you get a path report. But this is actually kind of giving you like specifically C function names and variables that hopefully, alongside with knowing things like, and U and 8 is a lot faster to add than a float, helps you, make RTL easier, essentially, like I've been saying. Righto. Alright. So that's all of the fundamental building blocks I want to talk about. And now I want to talk about some advanced features that I think are relatively unique to PipelineC, and I really enjoy using. So get into it. Global variables / clock crossings here. Alright, so first off, in green here, there can be multiple main functions. I may have alluded to that earlier, but now really getting to it, that when you tag two different functions as both being main, they're both top-level single instances that exist in parallel, and hardware description-wise, two module instances. But now we can do stuff in the global namespace to link them, like declare a global variable like so. And so, yeah, that globally visible and defined. And if you take a look on the left here, function A has some input argument, and what it's doing is it's assigning to that wire variable. And what that actually does is, in this case, it's making a wire out through the global namespace, between these modules here. And function B reads the wire here and uses it for its return value. So that wire gets routed down into function B and out the return value there. And so why this is neat, you can string these global wires kind of sort of all over the place. It certainly opens up the opportunity for all sorts of nasty, funny, almost go-to feeling, rat's nesty ugliness, but when used well, and some of the PipelineC examples are great examples of this. It can clean up code really nice and really composes nicely, and I've really been enjoying it. And so yeah, just to continue here, it's crossing hierarchy boundaries. If you had multiple nested functions inside function A and B, it'll make its way all the way up through multiple functions, out and all the way down into however hierarchy you have. It's doing things like checking that there's only one location that the wire is being written, but you can have multiple sides reading it. And now I've been calling this a wire here, and it's named the wire, the variable, and that's because these two functions are both at the same clock rate here. So wires between different clock rates are clock crossings, and we'll talk about that. But wires between the same clock domain are just wires. And yeah, to talk about clock domain crossings here, what you get if you're going between two main functions with an integer ratio frequency that are coming from the same PLL sort of deal, you can get deserializers inferred where, if one's 4 times faster than the other rate, you get one's got a 4 times wider bus than the other to keep a flow of data across the crossing there. Also for regular FIFOs, async FIFOs, you can mark paths as being async, like don't do anything special, ignore that this is a clock crossing between two arbitrary clock domains. I also note here that it's used for derived finite state machines. So on the next slide we'll get to talk about it. Let's see. Yeah, so let's see. So I had mentioned that you can do a lot of sort of arbitrary wiring together that could be kind of go-to-like in its messiness, but if used nicely, it can make for a really composable, you might say some of that stitching that you get from other sorts of tools. All right. Now we're getting into what I touched on in the last slide, derived state machines. So what does that mean? Well, now you can have functions with implicit state that derive state machines. And what's really neat about these is they have valid and ready handshaking, which we'll show on the next slide. But this is experimental for PipelineC, but Scilus, an alternative hardware description language that you should absolutely check out, knew about this as well and had a very similar clock step operator. So if you look at this green here, there's a function there that's representing this is the boundary between one state and another. This is the clock cycle boundary. So on the left here, there's no use of this clock function, and this is, as we've been seeing, just a basic pure function of combinatorial logic. Nothing special there. In the middle, though, you have your clock, and then you do this addition here, and your return of the output. And what that's doing is creating a state machine where one state is this function entry before hitting the clock, with nothing happens other than holding on to the value of x for the next cycle, the second state, where you're doing the addition and the output. And that's in contrast over here where we've moved that same green clock function there to be between the addition and the return. So in the first state, you have your addition logic, and then in this marked by the clock, in your second state is actually driving the return output. And so I mentioned this has valid and ready handshaking. So what does this actually look like here? Talking more about these derived finite state machines. So if you look at this main function here now, it's calling the two test functions from the previous slide, just one after another. And so over here in this diagram, you have an input handshake for entering this main function. And then from there, you're going into a state that's for the first subroutine call. And that's going off to the actual test one subroutine and back. And then into the second test subroutine and back. And then finally out of this function with another handshake. But to be more clear here, these functions are still modules. This is still PipelineC here, and functions are modules. So it actually is a main module, and inside of it is a module with a test 1 and test 2, but they're just not wired together with a kind of combinatorial logic data flow anymore. They're wired together with this state machine. And this is a logical state diagram, so that the clock from the previous slides is actually what defines the state. So the handshake in entering this main function into this test 1 subroutine, into the handshake of test 1, into its first state is all one clock cycle. And then the second state is that second state of test 1, leaving that, the output handshake, out that, in back through this submodule state, into the next submodule, and its first input handshake, and its first state. So you could very easily, as you might be seeing here, have long chains of combinatorial logic, but you can also be very expressive and compose very well complicated state machines. And the last point here, that each function call, as before, is a new instance. So if this was test 1, you wouldn't actually be entering the same state machine twice. We'll talk about that on this slide here for just a second, which is some advanced features that I don't really have time to dive in on, but I'll just touch on quickly here for you. So inferred clock enables. So I've been saying functions are modules. So what does it mean if you have if some condition, then your function module call? What you can't in Verilog or VHDL conditionally instantiate a module at runtime or something like that. But in PipelineC, that does have a meaning, and it, like it says, it ends up inferring clock enables for things. I had mentioned a few times that you can insert raw VHDL, and this lets you get black boxes in there, or IP you have existing elsewhere. You can use PipelineC to generate clocks. They don't all have to come from the outside, and you can do things with false paths and marking things as async. You can get into complicated things with feedback or in flow controls, where all of PipelineC's functions so far have been feed forward data flow. Maybe it has a register there for storage, but you can get non-registered feedback combinatorial loops. The star here from the previous slide, most of the time these derived state machine function calls are new instances, but you can actually tag things to say these specific functions are a single instance. Anywhere this FSM is being called, it's all talking about the same module, the same state machine, and so what that ends up doing is needing to infer arbitration, so multiple locations can share these state machines. And it gets into some really fun stuff where it starts feeling like threads and these shared regions, kind of atomically accessed. Some really neat experiments talking to remote systems, doing system calls and stuff like that in a state machine kind of look. Next point there, using the volatile keyword. I got to use the static keyword and abuse that a little bit, but volatile abused even worse, and there's some weird stuff that it ends up trying to do, and it's a fun experiment. And finally here, there is generated software C code as well. It's not a full system or system on chip or anything like that, but there are bits that help you shuffle structs through buffers and to and from the FPGA and stuff like that. And finally here at the bottom, just a clipping from GitHub here. There's some bugs floating around, but mostly I wanted to point out this enhancements bit here. I love talking to folks about new features and enhancements you want to see, or I want to write this C code and have it mean this, and is that a sensible model to be working with? Yeah, I love those kind of discussions. All right, last bit here is talking about an example project. And this is not just any example project. This is the most complex hardware demo that PipelineC has ever done, and I really need to take this time to thank Victor here. It wouldn't have been possible without him. We worked together for close to a year on this, and he wrote a ray-traced game specifically using PipelineC, and it compiles as C++ and runs in real time on a PC, because he also wrote a C++ parser and generator as part of his CFlex HDL project. And so that lets you write C++ that uses operator overloading on vector types and things like that that's not strictly C compatible, and then he generates C code that PipelineC can work with. We found a lot of bugs together and a lot of great optimizations we were able to make. Like I said, over close to a year of working together. It's really been wonderful. And thank you again, Victor. The specifics of the ray tracer I won't have a lot of time to get into today, but they really should be a whole talk of their own. Video is going to come through here on the capture, but there is a link there, and I'll be showing the link later. And this is Sphere versus Shapes. You're seeing Sphere, he's the sphere, and we're seeing Shapes here bouncing around, hoping not to fall through the floor. Check out reflections, obviously, in Spheri. There's reflections in the floor. There's a whole lot of things that I don't have time to talk about, and it's just a really fantastic demo. You can absolutely find more on Spheri versus Shapes out there. It did recently make its debut. Folks absolutely loved how power efficient it was. Custom hardware will do that for you, and yeah, it's great. Like I said, I don't have time today to dive into deep on how the ray tracer works, but I did want to share that architecturally, from the top level, it's not that complicated. There's 2 clock domains, so essentially 2 pragma main functions that you're dealing with. One here on the left, frame logic. That's stuff on each frame, so this is 60 frames a second, 60 hertz, and what it ends up being is just a really slow state machine. You're saying, position of the sphere at this frame, the next frame is some, computation, and that determines the position. If the button's being pressed, change the direction that the sphere is traveling in when it hits the floor, kind of logic, and no problem meeting time in there at 60 hertz. And so what you end up getting is, out of that is a wire coming out, and it's a global wire, so none of this needs to be routed through hierarchy or anything like that, and the game state is just read as a variable inside this other clock domain main function here, pixel logic, and that's actually things occurring at the pixel clock for this demo. It's 1080p, so it's 148.5 megahertz, and in this clock domain, this function, it's generating VGA timing, the V and H sync. It's counting off X and Y positions, and so that's what's being fed into the pixel rendering. So you say at position XY, and that's one pixel per one of these clock cycles is going into this render pixel pipeline, and then out the other end comes the pixel color and the rest of the VGA signals too. All right. And of course, finally, I wanted to touch on some future work for the project here. I'm always looking for help. I love discussion of new features and things like that. So the future is looking at things like improving the auto-pipelining. Right now, it doesn't optimize for area at all, or report it even. And then next is dealing with those feedback and stall and kind of potentially combinatorial loop signals opposite the normal data flow. Next bit is improving the derived finite state machines. The bits that are trying to share resources and arbitrate, and I had mentioned you get these long combinatorial paths when you compose state machines a lot of the time with their valid and ready handshaking. So a lot of improvement to be made there, and it's another layer of code generation in C, so that can use some cleanup as well. Next there is template types and functions. So there's no way, as in C, to parameterize functions here. There's no kind of compile time computation that would let you, change types or anything like that. So you're stuck doing things with a preprocessor, which, being a hardware person with C, sadly familiar with and have been doing. So next bit there, I'd mentioned that PipelineC, you can't just compile the entire design with a C compiler and try to emulate it or simulate it, but that certainly would be great. So that's certainly a goal. I frankly don't even have a working plan on how to attack that, which maybe might come into the next bullet point there, is getting into some actual hardware compiler frameworks that some wonderful folks out there are working on, like the Circ group and XLS from Google. So yes, plenty of future work to do. And all right, thank you folks for listening to me today talk to you about PipelineC. If you do have questions or comments, or you want to see more code, the main PipelineC repo is there. PipelineC graphics is what has the ray tracer demo code. Also has a link to a white paper with like a really detailed breakdown, some more videos. Victor's CFlex HDL project is there to check out. The video earlier that might not have come through in the capture is there to check out. I had done a previous talk about PipelineC and the ray tracer that goes into a bit more details that you can check out as well. Victor and I are on Twitter here, and come and talk to us on the PipelineC Discord there in the link. All right, folks, thank you for your time, and again, PipelineC, it's just easy open source hardware description between RTL and HLS. Thanks.